Welcome to our Solutions for NanoAnalysis podcast, brought to you by Bruker Nano Analytics. We look forward to bringing you a new podcast regularly. My name is Cody Morton. I'm a marketing communications specialist at Bruker Nano Analytics and an information enthusiast. If you like to learn from specialists in their field and hear what technologies are solving their problems, you will enjoy this podcast. Every session, we will focus on a different problem that our colleagues face in the lab and in the field. Some of the solutions will be a variation of ideas you may have heard before or even worked with. We will bring you these topics in a new and interesting way and introduce you to updated and thought-provoking results. We will talk about how the problem was dealt with in the past and what we're doing to solve the problem now and perhaps even envision future solutions. Join us as we talk solutions with a variety of scientists and technicians in many different industries in the Solutions for NanoAnalysis podcast. According to worldsteel.org, the birth of steel can be traced back to 13th century BCE. The invention of steel brought iron and charcoal together because early blacksmiths discovered that iron became harder and stronger when left in charcoal furnaces. By the 3rd century AD, China was manufacturing high-quality steel, likely having something similar to the Bessemer process that wouldn't be officially invented in Europe until the 19th century. In the 11th century, Damascus steel was a term used in Western culture from the medieval period onward to describe a type of steel created in India and would be developed and used in sword making. Jump ahead to the 18th century with the introduction of the crucible steel technique. All along the way, manufacturers have been working to perfect their process and to make a product that is strong, durable, and can withstand anything that industry can do to it. Testing has taken many directions, and scientists are always seeking ways to determine the soundness of the product. Scholars at the University of California wrote about a technique created by none other than Leonardo da Vinci to test the tensile strength of the wire with a suspended basket and slow pouring sand. When the wire broke, the basket clamped shut, and the experiment was reproduced with smaller and smaller wire to determine the ultimate strength and location of the fracture. While industry is creating stronger steel for more applications, the testing of this product must keep up. Today, we are joined by Geoff West with the University of Warwick WMG department to discuss how he and his students are testing steel in their lab. Thank you to my guest host, Tina Hill with Bruker Nano Analytics, and welcome, Geoff.
Great. Thanks, Cody. I am Tina Hill. I'm actually a geologist and an application scientist for the M4 tornado with Bruker. And we deal with a lot of different topics, different ideas. And today we're talking about Lowy mapping or Bragg mapping. And it will be a very interesting talk about some real applications. Geoff, would you mind introducing yourself? Geoff is a user of our M4 and has some real field experience, we'll say.
Yeah, hi Tina. My name's Geoff West. I'm from Warwick University, WMG department, and my role looks at, I'm responsible for the electron microscopy at WMG. One of the things that we've tried to put together is a kind of a full analytical workflow, which allows us to go from the macro levels where we're looking at many centimeters all the way down to the nanometer level TEM analysis. And we see the Bruker M4 tornado as a very important tool for the large-scale chemical mapping of our samples.
Thanks. And how long have you had your M4?
So we got our M4 installed January 2018. So it's just over 3.5 years.
Great. So you're probably familiar with my applications colleagues in Berlin, mostly, I guess.
Yeah, so before we bought the system, we actually went to Berlin for a couple of days. And we were very impressed with the knowledge of people like Weld. He was obviously very, very knowledgeable about the system. Yep. We didn't actually go there to look at XRF. We went there to look at microscopy accessories, but we were blown away with the capability of the XRF, and we could see some real applications for it in the kind of things that we were doing. So that actually became one of our priority systems based on that trip to Berlin. And that's actually when we first understood about the Bragg diffraction.
I was just going to ask when you first saw it.
because when one of the samples we ran, which is one of the EPRI samples, that they still show, we still see the data from that demo all the time that you guys show. We noticed that there's very good Bragg diffraction in that. And although during the demo they were talking about it as a purely artifact, it was clear that, yes, we wanted it out of the chemical distribution maps, but that information itself is very valuable as well.
So they actually showed you when you went and did the demo. So early on.
Yeah. So I think Weld was talking about how this, I think he was generating ideas and how you guys could use it for a positive purpose rather than just as a nuisance. And this was probably 5-6 years ago.
Yes.
It takes us time to get the money to get these systems.
It does, especially for universities, academic world. Yeah. So actually, TAP, Lola at EPRI, gave me your name, and that's why we're chatting today. I had come across his, the data that you mentioned and wanted to talk to him about it. And he said, oh yeah, you know what? I think you should talk to my friend Geoff. He's going to know a little bit more about it.
So I've worked with the guys at EPRI for about 10 years. TAP obviously hasn't been there quite that long, but the systems that we like and are systems that we're generating good results for them. We would like to be able to do that ourselves. And when they sort of said, look, we've seen the stuff we've been doing with DMWs, we want to be able to do that ourselves, I recommended they went for the Tornado Plus for them. And that, I know it has a lot of advantages, but for steels, I don't think the light elements does very much. I don't think the improved optics where you can look at bigger depth of field is particularly important. The biggest thing for the steels is the faster EDS processing power. Because I think that the electronics you've put in there are just way faster than the previous one. And that's what you want when you're doing steels. You want it to be fast. You don't really care about the size of the window because you're never worried about counts anyway. You're always having to tune the current down.
Right.
I said, look, the thing you need the speed of their electronics. And so I think that they're very happy with the system they've got.
Great, Geoff. We want to also know, what is the problem you're solving with this technology?
Yeah, so we'll take a step back. What do we use the XRF for on steels? Mainly we use it to be able to locally quantify chemistry of big components. Okay, so we can look at which bits have the positive and negative segregation. On a casting, that's quite predictable. We know roughly where it is. But then as it goes through the processing, and then we look at ex-service components, it can become a lot more complex, the variation in compositions. What the diffraction gives us on top of that is it gives us the relationship between the chemistry and the crystallography of the material. And that gives us a very powerful mix. And we always see the XRF as the first port of call. We get the overview of what we're looking at. You imagine you're looking at, you look at the stuff EPI look at. You're talking about, they have tons of material. Do we really want to look at 5 microns in a TM? Do we really want to look at a millimeter in an SEM? No, we want to look all the way through cross-section of their component. Which bit do we look at in more detail? Okay, and that first sweep gives us the overview of the material, often allows us to pick out things. We had a sample from EPRI last month. They sent us a sample. We stuck it in the XRF like we always do. And we're like, holy moly, what's all that massive niobium band down the middle? That doesn't look good.
Wow.
We'll have a look at that in the SEM. If we'd looked it straight in the SEM, we wouldn't have seen that. No chance of us picking that out. It lets you see where to look and where the potential problems are right from the start. And I know that you can do EDS mapping in the SEM, and you guys sell that product as well. But you try and do an EDS map in an SEM that rivals XRF, no chance.
Speed, sample prep, everything.
You just can't do it. I mean, we talked about this earlier, that people don't like the fact that you've got an interaction volume of 5 microns and that your spatial resolution isn't very good. But in terms of being able to map big things, these are real advantages. You're not getting bogged down. You're getting the average of a reasonable amount of material. It provides the extra sensitivity, provides a lot more power in terms of where you're going.
Well, and I think that particular EPRI map that we keep talking about, in my understanding, when you're looking at the weld, it looks as if there are larger crystals in the inner of the weld and then smaller at the edge. And my understanding is that's about cooling times. Did that end up being important in thinking about how quickly that cooled, therefore failure, or something different?
Yeah. So we've done a lot of EBSD mapping across the heat affected zone in the weld. That gives us obviously the more quantitative data on that. I think the thing is that, yeah, it does look really nice. But if you look at along the weld interface, the grain size change is quite uniform down.
Okay.
So it's quite easy to kind of map across with EBSD to actually be able to quantify all that. So it looks nice, but you don't get the same amount of understanding as you would do out of these casted things where you don't know what the hell the grain structure is going to look like in a really enormous part.
As a whole, yeah.
And the other problem with these welded things is the Bragg diffraction can be a bit misleading in a way, because the grain structure of steels, the orientation you get depends on the phase that's there. You can get different types of steels with different grain contrasts. We like to do that with EBSD. But you're right, it does look great.
Yeah, it's interesting. I guess coming in after all of that was done and sort of seeing the data, I was thinking that it was an area of actual failure. Is that the case?
Yeah, these welds always fail in the heat. So normally fail in the heat affected zone of the weld.
Okay.
It's quite normal.
So being able to see all of that is definitely an added bonus.
Yeah, I think that's something that EPRI could do more of, because I think that all they use their tornado for at the moment is looking for they're not really interested in segregation like we are. Mm-hmm. So they don't really care if they've got loads of diffraction artifacts in their maps. They can see what the composition of that weld bead is different to that one. They more do it from that perspective.
Do you think that they find differences based on grain size on the composition? I would think that would affect it a little bit. If they're looking only for composition, but yet they have a huge variation in grain size.
Yeah, so if you look at their maps, they have the Bragg diffraction superimposed on their segment on there.
So they can account for that.
But it doesn't really affect quantification so much. It just, on the visuals, it just doesn't look so good.
I suppose if you were looking for really, really precise and accurate numbers, that might be more of an issue. Yeah. But since they're not, no worries there. That was a good summation.
I may have missed it at the beginning, but was the micro-XRF M4 Tornado purchased for this particular use of working with steel, or was it thought as this was a technology that would also work for steel?
So the background to us getting the Tornado was I joined WMG in September 2015. And at my previous university, we'd just bought an XRF system. And we didn't actually buy the Tornado, we bought a competitor system. That wasn't just because we thought the XRF, the Bruker, was better, but the competitor packaged their XRF into a bigger package. And when I came to here, I was like, we should get an XRF because we've got the Advanced Steel Research Centre, your casting stuff, and you're interested in looking at the castings that we're producing. And it didn't take long for us to get some money from an XRF. And I wasn't actually involved in the evaluation this time because I'd already been to the evaluation and I knew that the Bruker one was best, even though we didn't get it last time. So I let some of my guys go and have a look. And they came back and said, we think the Bruker one's best. We should go for that. So we did. So yeah, it was bought primarily for looking at steel materials, although we do look at other stuff as well. And I think that I'm not aware of anybody else apart from us and EPRI using it for steels. I don't know whether you know anybody else. That surprises me because it's so powerful for steels.
So US Steel does have one here in the States.
Okay. Well, one of the things I've noticed how EPI operate the systems, and that, and I guess it's how we were told to operate them as well. There's a reluctance to use filters when you're scanning. However, when you're looking for segregation effects in steel, if you've got diffraction peaks in there, and these segregation variations are very small, we have to use the filters to get them out, because otherwise you've just got a layer of artifacts you don't understand on top of the maps. So one of the key things I've been telling them is, look, guys, you've got to use the filters for these distribution maps on steels. I know that perhaps it's not so good for the lighter element quantifications, but you've just got to take a hit on what you want, on what you need.
Right.
So I've been very kind of vocal in the use of filters, even though that does kill kind of the topic a little bit about what we're talking about today.
Yeah. But don't you think you really have to figure out the best way, the compromise to get out the kind of information that you want? So if you want to do Bragg diffraction, then you operate a certain way.
Yeah, so we're starting to do that. We're starting to do double runs, which is unfortunate, but we get some big castings. People want to know the chemical distribution and the grain structure. And we haven't figured out a way in which we can bring these two very divergent worlds together in an appropriate way. So we started to do double runs where we do it with the filters to get rid of all the Bragg, and then we do it without the filters to improve the light element performance and get the strong Bragg maps as well.
Mm-hmm. Actually, I do have a suggestion for you, but I don't want to talk about it just yet, because
it's going to be a long chat. I was so keen to do this because I think Tina's probably going to improve my world on this.
We can only hope. So the sample that you worked on with TAP, that was the first time you had thought about how to use this? And then did you come up with a project like right on the spot there, or did you have to marinate a little bit?
So they send us a lot of samples and we have quite a lot of projects with them. But they ask questions like, what's the composition of the weld metal? And if you've seen that demo sample, the composition of the weld metal depends on where you look. Okay. And one of the things is that you often get asked, what is the composition, or how accurate is that? And it doesn't matter how accurate your analysis is if the variation across your sample is massive, because getting a very accurate measurement in one location is meaningless if the whole part has a very varied range of composition. And that's the one thing we try and tell people, it's not always the average composition that's important. It is what is the extremes of composition. And that's what the XRF tells us. Parts never fail due to an average property. They fail because of an extreme. And compositional extreme is very important. And so we use the XRF a lot to locate the extreme locations in the sample. And they're the locations that we analyze in more detail.
So that's interesting, the way you say that, the extremes there. So did you run the sample a number of different ways to try and pinpoint those extremes? And then
no, so we just run it in the XRF. Once we've got that data, we know where the positively segregated areas are and the negatively segregated areas are. I mean, before we got the XRF, we used to assume these materials are homogeneous.
Mm-hmm.
And what we've seen since then, and we did a paper on this earlier this year, is that where you analyze is really important. If you're just analyzing random locations, you can get big scattering results, and that scatter is due to the compositional variation. So if you're smart about where you analyze, you can get rid of the scatter, and then you can look at what these properties are in a positively segregated area and a negatively segregated area.
Yeah.
So it's not just being able to measure the max and min composition. We can then take it further and measure the other things like the density of second phase particles, which is related to the composition.
Well, and that particular weld that we're talking about is a pretty stunning example of being able to see, like you said, the variation in composition, but then the Bragg maps are stunning. They're really fantastic. So that must have been a really interesting clue to you to see that and be able to.
I think the Bragg maps we got out of that really opened our eyes for the power of Bragg for these materials. I think for the DMW samples, like the EPI ones, the value in them is not quite so big because we know what the grain structure is going to look like. But when we're looking at castings and other components, there's a real interest in where, how does the segregation relate to how these grains have grown in the cast state. And we do a lot of work with Tata Steel, which is one of the biggest suppliers in Europe for steels. And they're co-located here at Warwick with us. And they ask us, look, we want you to show the grain structure on this massive, great 5 kilogram steel block. And we want to know the segregation in there as well. And we've tried etching it, but how do you etch a 5 kilogram block and then image it? How do you do that? It's right. It's so much easier just to stick it on the XRF and do a map.
Yes, definitely. So I'm curious to know when you did look at those castings, did you see? And I'm not an expert in steels, so forgive the question if it's a little basic. But the segregations that you saw in those, are the grain sizes much different than, say, looking at the EPRI samples?
So in a cast structure, you get different grain morphologies in different parts of the casting. It's about relating these different morphologies to where the segregation is occurring. And that's what is really important to understand.
So knowing, let's say, grain size in those different regions?
Grain size and shape.
And shape.
And because you get the elongated grains as well. So it's very useful for us to be able to relate those two things.
And what does that tell you overall? Let's say, are you looking for less homogeneity or less inhomogeneity or more for something like the casting?
So as a general rule, steel manufacturers like things to be homogeneous. But I think it's more a case of understanding it because things don't stay cast forever. So once they've cast it, then they do their forming processes. But it's important to understand what it looked like in the as-formed condition. And then you can see how that compositional variation changes during the processing.
So after you did some characterization for them, how did they use that information? Were they able to kind of pinpoint maybe some areas that they wanted to get much better feel for, or?
So the project we're doing with Tata is still quite early days, but we're using the XRF to basically, at the moment, pinpoint areas for more detailed study.
For other techniques.
Sure. And that's one of the things is the XRF tells us where to look. Instead of, needle in a haystack, we know this area has this grain structure and has this composition.
Right.
Instead of, you've got the helicopter view of what's going on.
Well, and I think that idea really resonates in pretty much any industry that the M4 uses, because it is such a quick way to take a look at something like that so that you can delve in deeper. I mean, geology, of course, comes to mind with their cores. You want to do the same thing where you want to see the inhomogeneity and identify those places that you want to look at a little closer so that you can either figure out if it's where you want to be or where you don't want to be.
Well, I'm actually very surprised at the small number of these systems in steel research centers.
Do you think it's just a matter that people haven't really thought about it before?
I think it's, well, my personal view is that the reason why there's so few of them is because if you look at the specifications on an XRF, they look terrible because you've got spatial resolution of 25 microns. That doesn't excite people. They're thinking, well, in their minds, they're thinking that spatial resolution doesn't work. They don't realize that you need that higher spatial resolution is not always good.
Right.
Okay. And I think that mentally that people struggle with that concept. And I think when they look, why am I buying a system with such poor spatial resolution? I think that that's a very hard thing for them to understand.
Well, I think especially people get into a mode. This is how we analyze it. This is the information that we get out. And it's really difficult to look at something like Bragg diffraction and say, wow, I think we could really use this to our benefit and change the way they do something like that.
Yeah, I mean, I just see Bragg diffraction as just you wouldn't buy the system for Bragg diffraction,
right?
But it's just a nice little complementary technique where you can get the chemistry. It's like combined EBSD, EDS. You've got both. You got the chemical and crystallographic information all in one hit,
right?
And I think that that's very powerful. I genuinely believe people don't look at these systems because they think spatial resolution's terrible. And it's basically an EDS-based system. They don't understand that the sensitivity is so much better.
Yeah, that's an interesting point of view, actually. I hadn't really thought about it like that. Do you use diffraction, like XRD, on these types of samples? Did you do that before?
So XRD doesn't really do much for us because we know what phase it is.
Sure.
So we've got very good XRD facilities here at Warwick. We've got a few Bruker systems, actually. But yeah, we don't tend to do much on these steel samples because we know what the phase structure is. And the second phase structure is a volume percent that XRD is not good with.
Sure, that makes sense. So what are the samples that you're working on now that you mentioned to me?
We use any sample we get from EPRI, we always stick in the XRF. It's just so that it's just our routine, because we know that the stuff they give us is normally quite high alloy materials, and so there's going to be segregation effects. So any sample that we know is quite a high alloy, we will just stick in XRF just to check it out. Does that flag anything up? So we use it as a first port of call for a lot of the samples that come in. We do quite a lot of external work on the system. So places like Manchester University, I don't know whether you're aware of Manchester, they've got the biggest materials department in the country, in the UK, and they have every system known to man, but they don't have an XRF system, probably for the reasons I mentioned earlier. Sure. We do a lot of XRF for them, and we do XRF on the castings that we produce in-house as well.
And so are you looking to figure out how to do composition and diffraction at the same time for everything that you're doing? I mean, all of these things that you produce and the others that come in.
Yeah, so I mean, we always see that in any situation, we see that the Bragg diffraction, if it's not in the maps we want it to be in, as a benefit, if we can get a map that shows the grain structure alongside, there's never a disadvantage to having more information, as long as it doesn't intrude in the information that we want.
Right. Well, I'm curious to know, because the Bragg peaks can show up somewhat consistently based on the types of materials that you have. I'm guessing that since you know the phases, you know what you're looking at a lot, maybe you see some consistent locations of Bragg peaks, but what do the spectra look like? Is it always just kind of a crapshoot for you, or are you looking for some very specific ones every time?
So I think one of the problems we have is that in a lot of the steels that we look at, elements that we're interested in, things like niobium, molybdenum, so quite heavy elements, which are in the range where diffraction peaks are quite likely to be present. Sure. Okay. So you said before that your metallurgy isn't perfect. Things like niobium and molybdenum are the biggest segregators. They're heavy, they're big, they're immobile. So they're the ones in a lot of steels that we're particularly interested in because they're easy for us to spot, and they're very important for the understanding the segregation behavior of these steels. So consequently, we don't want any diffraction to kind of interrupt our interpretation of these ones.
Right.
So we tend to use quite thick filters to ensure that and we still get a decent rhodium signal on a lot of samples, and that often gives us some diffraction. But if we take away the filter and run it, our Bragg looks way better. There's no question about that. And we were looking at some samples last week for a company in the UK. And for some reason, I don't fully understand it, but the rhodium signal was not very good. But copper, we got unbelievable diffraction contrast in the copper peak. It seemed to move depending, because we were looking at a different composition of alloy. I guess that's quite normal, is it?
The Bragg peaks moving because of different composition?
Yeah.
Well, I would think that the crystals would be slightly different angles, different locations, different sizes based on the composition. Is that?
Most of the materials we look at, the rhodium fraction is always the best one. But for some reason, these strange alloys that I was sent, copper one was really good. It's the other thing that I haven't fully got my head around. Is one of the selling points to XRF is that sample preparation doesn't need to be great.
Mm-hmm.
Okay, and obviously I think people often take that too literally.
Yeah.
Because for steel, we always see that the interaction volume is something between 5 and 10 microns, something like that.
Mm-hmm.
Okay, so if you want nice Bragg diffraction, if your sample has got a pile of cold work in the surface, loads of deformation, I can't see how you're going to get good Bragg diffraction, because you're not going to have a clear grain structure there. So we tend to prepare our samples, even the big blocks. Yeah, we wouldn't want to stick it in a microscope and do EBSD on it, but we try and prepare it. We don't just grind it and then stick it in. We try and get the preparation to be as good as we can in a reasonable time period, just so that we haven't got a smearing effect, and that we are giving ourselves a chance with the Bragg diffraction. But the quality of the Bragg diffraction we get does seem to be variable, and we don't understand fully what we need to do to make. We understand that sample preparation probably needs to be reasonable, but we get some samples where we get really nice Bragg diffraction even with filters. Mm-hmm. And then we put a sample in that we think is very similar, prepared very similar, and we just don't get it. So there is some variability with it that we just don't understand. So I was very keen to hear any kind of recommendations you had in terms of how you would collect data that didn't have the Bragg in the maps that you wanted to show the variation, but did allow you to see the grain structure.
Yeah. So first, I am very interested in the idea of figuring out how to maximize that property. And it's not something that I've done a lot of work on, but I am really curious, because I think understanding how you end up with these based on the sample you have and the preparation that you have affects that could really be something that makes life a little bit easier for a lot of people. It would be an interesting study to see what kind of samples would be best. I mean, obviously we know larger crystals are probably going to diffract better. Yeah, that's probably a big one. And I suppose the composition for sure would make that. But I don't know how you would figure out, there's probably a way to figure out the likelihood of what you have diffracting. I don't know, maybe I'll think about that a little bit.
One other question that I had was, some scientists, Geoff, maybe one of these types of people, have run samples in the micro-XRF just for fun, just for, hey, I wonder what this looks like. Have you run any samples that you were surprised? Other than steel, have you run any samples to just see what the technology will do that have given you any surprises or interesting results?
I'm not sure. We do look at other biosamples with staining. We've looked at WMG. We have big SME team. This is a team that looks after small and medium enterprises. Basically, the idea is it makes the small guys, helps them become better. And they use the XRF a lot on a lot of samples that their customers have. But because I don't have so much background on what the hell we're putting in, I don't really get that surprised by what comes out. If you know what I mean? I don't really have you don't tell me enough about the sample to surprise me. We have looked at superalloy samples, and they're always really interesting to look at because superalloys are a really interesting mix of different elements. And one of the advantages of the XRF being 50 kV is that it's so much easier to work out the composition of these things because you can look at all the higher energy lines. And I never realized just how heterogeneous these things were until we started looking at them in the XRF.
Yeah.
And I think that kind of really opened my eyes that, look, when we analyze these samples in the SEM, we just need to be a bit more careful where we're looking.
Do you use standards at all? Because a lot of people say the same. Everyone assumes that most standards are very homogeneous, but when you start looking at them in the XRF, sometimes you find that they're not.
So EPRI have given us a standard. And one of the things that we're trying to do is we're trying to improve. So the XRF quants that we get are good, but they can be better.
Mm-hmm.
So we get different results depending on what filters we use.
Yep.
Certain elements underestimate reproducibly depending on what filters and stuff we use.
Right.
And so we're trying to figure out a way in which we can account for that.
I'm sure that I could come up with a million more questions, but...
Well, I just wanted to have a quick follow-up question. If someone is interested in finding out more about steel analysis with micro-XRF, Tina, I believe we have a abstract available that we can point to online in our show notes. Is there anything, Geoff, that you have released or published or know about that talks about this topic as well?
We recently published a paper about the effect of segregation from 9-chrome steels, similar to EPRI. So it's published with the guys at EPRI. And in this paper, we show XRF result. And I can send you this paper if you'd like.
Yeah, that'd be great. Or a link to it.
Is this the one that was fairly recently published? It might be the one that I helped tap with. No,
so that one was all about some case studies looking at XRF.
Yeah.
This is separate from that. So the results in this one are, so basically we've looked at a forging and we've looked at a pipe. And in the forging, you've got these clouds of segregation, which you can see very clearly in the XRF. And in the pipe, you've got these stripes. And what is actually my PhD student, he's quantified the second phase particles in a cloud and away from a cloud. And he's shown that the numbers he gets are completely different. And what he's shown is if you just randomly collect the images, you get a nice big scatter. And if you collect from a negative and then a positive one, you get the extremes of the scatter. So the scatter doesn't have to be there if you think about where you collect in terms of composition. And we did that on the easiest particle is to measure. What we're doing now is we're trying to do this on more complicated things like inclusions and things like that.
Where's that paper?
I will send it to you.
Oh, thank you.
Is it available online at all, or is it just...
It is. But if I send it to you, then you can try and look online as well if you want.
Thank you so much, Geoff. We really appreciate your time. Thank you to our speakers today. If you would like more information about today's topic or to submit a topic idea, please email info.bna@bruker.com. You can also check out more information in today's show notes. Join us next time as we look at a new solution with more scientists and technicians in all sorts of industries.